And don't forget the charges on ions. To make these equations a little easier for us, I got a deal for you. Are you ready? This deal only is good until the end of May. After that, all bets are off. In other words, you can't use what I'm talking about when you take your college chemistry class. Okay? In this class, the only place we're ever going to see ions, individual ions, is in aqueous solution. We can put ions together, positive and negatives together, and make a neutral compound in an ionic compound. But if we're going to see ions, separate independent ions, in this class, they're going to be dissolved in aqueous solution. Right? So here's what we'll do. Since if we can all agree that that's the case, then we don't need to write aqueous symbols under our ions then, do we? That's the only place we're going to see them. Now again, you're not going to, you know, when you're in Berkeley at your chemistry class, freshman chemistry class at Berkeley is run in 2 auditoriums. They each seat 500 students. One auditorium looks at TV monitors of the professor in the other auditorium.
How big are those TVs? You don't have questions.
Yeah, you don't have to.
It's interesting to me that the universities that we think of as prestigious universities that everybody tries so hard to get into can be crappy in a couple of ways. If you took freshman chemistry at the junior college, which everybody looks down their nose at, you're in an auditorium with 100 to 125 students. And you can actually raise your hand and ask a question. And the professor who teaches the course will actually meet with you during their office hours.
Oh my God.
If you go to Berkeley, you're going to be in an auditorium with so many people there's no way you could ask a question. And the professor does not make themselves available to you being just an underclassman, you know, being an undergraduate. They spend all their time with their graduate students. Now there are some advantages to going to Berkeley over the junior college. There are. One of the things that determines quality of experience is the other students that you're with. When you go to Stanford, one of the advantages is that you are with the top 2% of high school students, because that's about all they accept. And that raises the level of everything, right? That's good. But it's not all good. So, we want aqueous symbols here and here, because neutral molecules could be in any one of the 3 states, solid, liquid, and gas, or be dissolved in solution. So that would be a spontaneous acid-base reaction that involves these 2 bases. Yeah? How we doing? And how would I carry out this reaction? What would I make? First of all, I'm going to make solutions, aren't I? I'm going to be pouring 2 solutions together to make this reaction occur. I need to find some nitrous acid and dissolve it in water. I don't have a nitrous acid solution, but I can buy one. Okay? And we would dilute this to whatever concentration we decided we needed. And how would I make this solution? Sodium acetate dissolved in water, and I have sodium acetate. That's what we use for the supersaturation demo, for instance. Yeah. So I would get a solution of nitrous acid, dilute it to whatever I wanted it to be. I would take some solid sodium acetate and dissolve that in water to make whatever concentration solution I need to make, and I'd pour those 2 solutions together, wouldn't I? Okay? How we doing?
So you just have sodium with it because it wouldn't react with anything else.
Because we can't have negative ions without positive ions. I can't have a liter of solution that has dissolved in it just negative ions. That won't work. Negative ions repel each other. They'd be jumping out of the water. Would be, I guess. We wouldn't be able to see them, but what would happen if you had, you know, you've seen a bolt of lightning before? A bolt of lightning involves less than a mole of negative charges.
That's all lightning.
So if I had a liter of solution with a mole of negative charges in it, would we expect a bolt of lightning to jump out of that?
Really big bolt of lightning.
Yeah. Yeah. The bottom line is, no, we can't do it. No, we're not going to do it. The reason we can't do it is because it's very hard to get that many negative charges in one place without something close to that many positive charges. Rub your feet across the carpet, touch the doorknob, you get a little spark. You've rubbed a few million extra electrons on or off of your body. And a few million seems like a lot, but it's not. Huh. The number of electrons in your body would be measured in the tens of thousands of moles of electrons. And that's in the neighborhood of 10 to the 27th. Millions would be 10 to the 6th. How big is 10 to the 6th compared to 10 to the 27th? 10 to the 27th is 10 to the 21st times bigger than that. 10 to the 9th is a billion. 10 to the 18th is a billion billion. So that would be 1,000 billion billion times what we're talking about. So a few million electrons is not hard to get. And I can have a few million negative or positive ions someplace, that's not a problem. But that's not even close to what we're talking about here. Not even close, right? Okay?
So as you put more and more moles of negative charges, it'll just make bigger and bigger bolts of lightning?
Well, again, we can create bolts of lightning. A Van de Graaff generator will do that. We have a Van de Graaff generator that'll generate sparks about that long.
Here?
In the physics lab next door. They have Van de Graaff generators that are really big that create bolts of lightning that are 30, 40, 50 feet long. You know, it's hard for humans to create the kind of lightning that we see in the sky.
Right.
You know, you need a really big scale to do those sorts of things. Okay. So, what would happen if I took sodium acetate and dissolved it in water? What would change? First of all, when I dissolve this in water, I would be making separate sodium ions and separate acetate ions, right? What do we have in water already? If I had pure water, is pure water pure water? No. Is water an acid?
Yeah.
Yes.
Is water a base?
Yes.
In other words, water is butyric. And because water can act as an acid and a base, in water, pure water, water molecules are bumping into one another, and occasionally one water molecule will steal a hydrogen ion away from another. So water contains hydrogen ions, well, excuse me, hydronium ions and hydroxide ions. A little problem because I'm teaching acid-base